Welcome back. Measuring strike and dip. Now, some of you have discussed this in your 1010 geology introductory courses. Others may not. You're a little bit lost. What in the world is strike and dip? Well, strike and dip is something that geologists absolutely love and love to measure. And so let's go over a little review and then explain in detail how you measure strike and dip. Okay, concept of strike and dip, it's geologic. It's a geologic data set that has to do with folds and tilts. So what is it? Well, first of all, preamble, to measure strike and dip, you will need a compass. Aha! You say. The Brunton. Absolutely correct. But there are two types of Bruntons that are out there, or two types of compass systems. Right? The first one is called an Azimuth compass. An Azimuth compass has a 360-degree reading. Once around is 360 degrees, usually goes clockwise from the 12 o'clock all the way around back to 12 o'clock, 360 degrees. The other one is a quadrant compass, and it is subdivided into 4 quadrants of 90 degrees each: the northwest quadrant, the northeast quadrant, the southwest quadrant, and the southeast quadrant. These are the two scales that are often used in compass or transit applications. Now, remember, for compass, basic is north is up, right? South is down, east is to the right, and west is to the left. So this is a common compass layout in your dial that you will see. And in azimuth notation, of course, starts at 0 and goes around clockwise to 360. And you can then take the readings with your compass needle as it points to these various degree subdivisions. In a quadrant notation, we have each one of these 4 quadrants divided by 90. North and south are always 0, and then to the left or right, in both cases, we increase to 90 in the east or western designation. We can easily take a quadrant notation and actually divide it into quadrants, and you can see I have the northwest quadrant right here, the northeast quadrant right here, my southwest quadrant in this area, and the southeast quadrant in this area. All right, and this is, of course, the geologist's preference. Actually likes a quadrant notation, with the northern quadrants being the preferred data recording modes. Hence, we are trying to, when we purchase a Brunton, we are trying to get the quadrant Bruntons. They are not quite as popular. Azimuth is used more often because azimuth is used in orienteering and orientation. But the Brunton compass, we're trying to have those that use the so-called quadrant notation. And what you do with a Brunton, well, you're going to use these measurements to actually record readings in the field. And you will do that. And this is basically the heart of the Geology 2530 class, is doing a lot with the Brunton instrument as your reconnaissance geosurvey tool. Okay, back to strike and dip. Let's give the explanation of strike and dip. First of all, what in the world is strike? Well, since we're using a compass, you know it has to do something with the compass, and strike is defined as the geographic direction, if you want the azimuth, of an exact horizontal line drawn on the sloping side of a tilted rock outcrop. So if you have a tilted rock outcrop and you would draw an exactly horizontal line on that tilted rock outcrop, the direction, the compass direction of the tilted line would be your strike. Right? What is a dip? Well, the dip is a direction of water running down the sloping side of your tilted rock outcrop. Okay. It also has some steepness to it. These rock tilts can be very steep and very gentle, so it must have an angle measurement of how steeply your rock tilts. Well, strike and dip are always perpendicular to each other. So once you get the strike figured out, you know that the dip must be perpendicular. If you have the dip figured out, you know that the strike must be perpendicular. So this is really helpful as you process strike and dip readings. Now let's look at something simple that explains the concept of strike and dip. Let's say you have a regular saddle roof on a house. Well, the roof saddle right here, the convergence of both of my roof sides would be the strike direction. And of course, in both directions, I would have the dip direction from that strike. Perpendicular to each other, right? That's my roof saddle right here would be then my strike direction. Now, the question always arises, how do you get a perfectly straight line on something out there in an outcrop? Well, if you have water, like a lake, this is cool, because water will always draw a perfectly horizontal line on any outcrop. So here's a lake with some dipping strata, dipping beds going into this lake, and there's sort of my shore zone, my beach, of course, is solid rock. There's no sand there, and you can see that line that the water draws there on this tilted rock outcrop would be literally my line of strike. That would be the strike line. So you have to picture water everywhere when you go out and see what would be the shore at a perfectly quiet mirror-like lake on that outcrop. Of course, the dip then goes from the horizontal water level downward, like 30 degrees, 20 degrees, 50 degrees, whatever the dip or tilt may be. And the tilt, of course, is perpendicular to my strike line, as you can see. Now, how do you measure and record strike and dip? Let's try to do this, by measuring and mapping. Well, I have my lake again. I have my inclined strata. I have my dip 18 degrees. If I measure this and the dip, how do I write it on a flat piece of paper? Now, maps are a flat piece of paper, and you cannot see rock tilt on the map. I mean, sometimes you can imagine it, but if you have a strike and dip symbol on the map, you know what the strike line is and in what direction and by how much it is dipping. So here's a map strike and dip symbol. Looks kind of like a little lopsided T. That's my T bar, very, very long with a tick mark that goes downhill perpendicular, and the number there indicates by how many degrees it tilts actually into the ground. Remember, strike and dip are perpendicular to each other, and you can see this here quite nicely. Now, in the three-dimensional objects, it somewhat doesn't make much sense to do it this way because you can see it, right? If I had a tilted rock outcrop like here, a horizontal line where the water would go and then my dip, I mean, you can see it. But what if your paper was flat? What if you had a flat piece of paper, like a geologic map you would see here, and it's full of strike and dip symbols? Now you know which way my rock layers are tilting. They're tilting into the, what would that be? The south west quadrant into the ground. All right. Now this is how you would draw a strike and dip symbol in a map, but how would you write a strike and dip notation on a written piece of paper, like your notebook? Well, let's do this. Strike direction. For this particular one, what is a strike direction? How would I write this as a shorthand notation into a notebook? All right, let's enlarge this strike symbol, strike and dip symbol a little bit, but make it larger, right? And we're going to put our quadrant compass right on top of it with the crosshairs in the middle. All right, good. So let's read off the strike direction, which is, of course, parallel to my long T-bar here. And remember, we say the northern quadrants are preferred, so it's not wrong to use it down here, but I'm going to stick with the northern quadrant systems here. And what I find is that here's my north, and then it deviates from the straight north a certain amount of degrees toward the west. That's where my arrow points to, into the northwest quadrant here, right? So I point into the northwest quadrant, but I deviate a certain degrees from the north into this quadrant. So I need to write a number in the middle between my north and my west. I already know it pointing into the northwest quadrant. Well, I can use a scale here and tick it off. This is north, 10, 20, 30, 40. There's 50. Half between 40 and 50. Probably 45. So my written shorthand designation for that particular strike would be N45 west, or north 45 degrees toward the west is my shorthand strike designation. What about dip? Right? That's my written strike notation right here. What about my dip notation? Dip direction and angle. Now, I already have the perfect aligned compass direction given me in the strike. So I do not need a perfect compass direction for the dip anymore. It's already perpendicular. 90 degrees. It's always, always, always 90 degrees offset or perpendicular to the strike. So I just need to indicate in which general quadrant my dip is going. I have two choices here. I could go in the southwest quadrant or the northeast quadrant. I need to indicate which one of those two it's going to be. So I know it's 30 degrees down. I write this one down, and then I just label it in the tick mark in which direction it's going in my southwest quadrant. So I would say 30 degrees into the southwest quadrant, and this would be exactly how I would write down my dip notation. So I have a written strike notation, I have a written dip notation. My strike is north N45W, north 45 west. My dip notation is 30. You can even leave the degree sign off, but 30 into the southwest quadrant, 30 degrees into the southwest quadrant, 30 SW. Of course, if I slice the whole thing open, I would get the picture. So here's a cross section, dips 30 degrees down. If my ground is flat, this is what I would see if I would look right on, straight onto the strike direction, or really parallel to the dip direction. That's what I would see as I would slice the ground open. Okay, I got a little practice question for you. Here's a strike and dip symbol. I've given you faintly an outline of the compass designation here. And so using a quadrant notation, was preferred the northern quadrants, right? What is my strike and what is my dip? You may pause the video and I will give you the answer in a second. Okay, answer. 10 degrees off from the northern designation into the points into the northeastern quadrant, so N10 east would be the strike direction. My dip direction, 45 degrees, into which quadrant? Into the northwest quadrant. Even if it's just a little tiny bit, just a few degrees, give the quadrant designation. You don't have to be exact anymore by how many degrees does it do that. Remember, this is perpendicular. Strike and dip are perpendicular. You just need to give me the general direction. So 45 degrees into the northwest quadrant. This is what it says, right? So practical stuff. Now, what's the theory behind it? Before you can use a compass, something called setting the declination. What in the world is that? So this may come as a surprise to some of you. The geographic north, the one you see in the map, the one that is actually where the North Pole is supposed to be, according to survey, the Earth survey, is not the same as the magnetic north. You may say, I've got to be kidding. No, they don't overlap. Actually, the magnetic north wanders around, and as you know from your geology studies, they sometimes flip polarity completely. The North Pole wanders, the magnetic North Pole wanders to the South Pole, and the magnetic South Pole wanders to the North Pole. But here's the deal. They've tried to track it since, the 16th century on. This has been kind of the path of the magnetic north over time. In 1859 it was here, in 1904 it was here, and now it's somewhat consistently kind of wanders along this path. Here would be your actual north, your geographic north. And this is sort of where that sucker has been wandering ever since. So your compass needle is not pointing to the geographic north. It's, of course, what you want. Oh. So here's a more modern map, like from the last century into our century now, up to 2020. You can see in 2015 or 2020 we had this magnetic north kind of wander, and it's projected to do the same. I don't know, it might go over into Russia eventually, who knows, but it has been wandering around. So what that means is that when you do compass measurements, you have a variation. You're supposed to point to the true North Pole, but instead your needle points to the magnetic north, and so you're off. Your measurements are going to be off. That sucks for accurate measurements. Is there any way we can fix that? Yeah, we can measure that difference. We call this a declination. That is declination. By the way, if it goes to the left, the magnetic north is to the left of the true north, they call it a negative magnetic declination. If it goes to the other side, to the right, it's a positive magnetic declination. And, of course, that angle, the declination, can vary depending on where you are on our globe. So, compass needle is off from the true north by a certain degree amount called the declination, or D, right there. And the question then arises, how do you know how much D that is? How do you correct for it? And is it a D plus, like in this direction, or is it D minus going on into the other direction? What is my declination offset? Well, to figure this one out, we get a little help. We have something that is produced regularly, about every 10 years or so. It's called an isogonic map, and the map shows declination lines. All right, well, we have no declination where the magnetic north actually coincides with the true geographic north. It's called a agonic line. Well, that's 0, and it goes right through these states. So if you're in Illinois or somewhere, you will be on that agonic line. But if you go to the west or to the east, we have a variation. And so how would you figure this? Well, you find your place where you are, and then you see which line comes closest to where you write on it. And then you can set your compass according to that deviation or declination pattern. By the way, an isogenic map is given in your Field Methods Handbook on page 12, which I have reproduced here for you. That's much more detailed. You can see this. Here is my agonic line. Right, that's 0 where it coincides. And then these lines here, the 10, 15, is by how much my measurements are deviating from the true north. So if you want to set your compass, you need to figure out where you are. Of course, we are in Colorado, that has the possibilities of these isogenic lines that we could use or set our compass to. And of course, this is a front range, so we are somewhat cruising around for this class in that area, which gives me a adjustment or a declination, a deviation from a true north of minus 9 degrees. Right, negative minus 9. Okay. Now, we know that. We figured this one out. Of course, if you travel to Utah or to western Colorado, you will need to reset your compass. Grand Junction would be then a minus 11. If you're like in Moab, you're closer to a minus 12 and so forth. Now, rounding it to a full degree is totally okay. Measurements would probably not be more accurate than that, but it gives you some idea of what to set this one to. Now, how do you do this on the Brunton? Well, if you look at the Brunton, it has actually a circle adjusting screw right there on one of its sides. You can tweak this with a coin or even with a fingernail, and what you will notice when you do this, your whole dial, the whole compass dial starts rotating left or right, depending which direction you're going. So while you're turning this one, you of course need to look at the front of the compass, and you may see something like this. There is a metal pin right there. It's called the 0 pin. It sticks out there. And so if you have no declination, or like on this line, you would set the 0 right onto this little beast, seeing right here, onto the 0 of the compass. So there is no change. But if you're in somewhere this field where there is a declination, you have to kind of tweak it and make this pin either move to the right of your 0 or to the left of your 0. And the question is, with a negative 9, where does my pin need to be, to the right or to the left? If you can try to think with me, I will give you the answer, of course. For us, it needs to sit to the left of the 0. Now, here it shows 15 degrees east, or east is usually the negative designation. West would be the positive designation. Of course, you would set it to 9, which would be right there. So you need to tweak this little dial, the little screw dial, until your pin sits right at the 9 degrees to the left of the 0. And then, when you take measurements, they're adjusted to true north. Now, you don't have to do any fancy calculation. The compass is set to that. Now, when you now look at north, it points actually to the true geographic north. And this is kind of cool. Now, your Brunton Geolite does not have the screw, but the ring there twists, so you can twist the whole ring and basically do the same thing, adjusting the magnetic declination, which is usually the deal for the higher grade, the more advanced compass or transit instruments. Now, quadrant versus azimuth. We already said that geologists prefer the quadrant. But what if you have an azimuth compass? Unfortunately, and I don't know why, maybe they will come out with those later, the Brunton geolite is an azimuth designation only, which is rather sucky. So you need to convert. You need to convert. If you have an azimuth compass, and even from our loaner compass for Bruntons that we give out, you might grab an azimuth, and all the other ones are gone, and saying, okay, how do I convert? Well, you need to go from this notation, from 0 to 360, to this notation. How would you do this? Well, luckily, there is some equations you can use. They're very, very simple to use. They are also in your field notebook. Here is the conversion equation for each quadrant, as you see here. So if your azimuth reading is between 0 and 90, you would use this equation. If your azimuth reading is between 270 and 360, you would use this equation, and so forth. And it would give you then that result. Let me show you an example. Best to do this by an example. So let's say your azimuth reading is 247, like shown in this picture here. What's your quad reading? What's your equivalent quad reading? So first, let's see which range you fall into. 247 falls into that range, 180 to 270. All right, so I'm going to use this equation. What do I need to do? Well, where you see the X with a degree sign, this is where I need to plug in my 247 right there, and then subtract 180 from that. Well, that was easy, right? Okay, so let's do this. If I subtract 247, 180 from 247, I get 67. So my compass designation in the quad notation would be south, 67 west. Big deal. Very simple. Hey, wait 1 minute. Geologists prefer northern quadrant designations. I have a southern quadrant designation. How do I convert the southern quadrant to the northern quadrant? Very simple. You can use it optically too. Convert south 67 west to a northern quadrant designation. Well, draw a line straight across. Exactly the opposite would be the same right over there. So it's actually fairly simple. It's the adjacent, the kitty corner quadrant on the other side, north 67 east. So south 67 west is the same as north 67 east. Not a big deal. Not a big deal at all. Kind of convert these designations as you record them. Okay, now in your fieldwork handbook, page 14 has actually a reprint of that picture down there, so you can have it always with you and do the conversions on the fly in the field. Now for dip, there's something some of you may not know that makes readings incredibly accurate. It's called a vernier scale. So what is a vernier scale, right? Let's take a look at your Brunton, a regular Brunton. You see the clinometer bubble. We talked about this. You have a percent grade scale, cool for engineers. You have the actual degree grade scale down here. And then you have this funny thing. This is called an arc minute vernier. This 0 to 60 in both directions are arc minutes. 60 arc minutes is equal 1 degree. So this is a vernier. Let's see how you operate this one when you take a reading. All right, so here is my little zoom in enlargement. First of all, a little background here. Do not use this scale. This is a percent slope scale. This is rarely used. You use this one in constructing roads, like the road sign when it says you have a 12% gradient on that road or 8% gradient. This is what engineers would be using. So we rarely use a percent scale, so you can kind of ignore this one. But what you will use is this one here. that is my degree scale, and we want to give the dip angles if we ever do them in degree. Okay, so on that little beast right there, it looks kind of strange like a butterfly, is called the vernier scale in 60-minute designation. So right here would be half a degree, or 30 minutes, and 60 degrees would be 1 full degree. It's the arc minutes. Yeah, we are borrowing the time units for angular measurements as well. So let's take a look at the reading. And at first, I want to kind of look at this big fat line right there and see where it lines up on my degree scale down here. So it lines up. I can see this is 10, this is 20, 11, 12. So somewhere between 12 and 13, you can see that. So I know maybe it's a little closer to the 13. Hard to tell, but that's what I assumed. So it's closer to the 13. But then I need to subtract a little bit. I just don't know how much that a little bit is yet. So I need to subtract a little bit to get the actual angular reading. So it's between those two. This is where the vernier scale comes in. How do I figure this little? Well, the way to do this is to find the best match tick between the vernier and the degree scale. What does it mean, best match tick? So you have tick marks right there on the vernier scale, and you have also tick marks on the angle on the degree scale down there. So it doesn't matter which one. Let's look at each one of those and see which one has a perfect match equivalent on the other side. Well, this one is close, but still offset. And these are more offset. Looks like I found one right here. See that? Perfect match. That's where these two line up. Perfect match. So what does that mean? Now you read the vernier scale. Remember, for the 0 line, the fat line, you use the degree scale. For that perfect match now, you're going to read off the vernier scale, and looks like these are all given in 10 arc minutes. So 10 arc minute, 20 arc minutes, 30 arc minutes, right there. 40 arc minutes, 50 arc minutes, 60 arc minutes. So this is the 40 arc minute line. So my little here, right, the vernier arc that I am reading off that I need to subtract from my 13 is going to be 40 arc minutes. Well, 13 degrees minus 40 arc minutes, I know 60 arc minutes equals 1 degree, gives me 12 degrees and 20 arc minutes as the exact dip angle. Now, it's amazing that you can use this little instrument that accurately. I tell you right now, usually round to the nearest degree. No, you don't need this exact. Usually you need to have some kind of a tripod or something to get to make this really, really useful. But I'm just telling you, this is how the vernier scale is used. So that would be my exact reading, 12 degrees, 20 arc minutes. I would just round it to 12 degrees and record that close enough, right? Now, by the way, if you go into this direction, you're going to subtract from the higher of the two numbers it sits between. So if you go to this direction and your perfect match is here, like we have it, I would then subtract that from the higher, which was 13, of the two numbers my actual degree line sits in between. If I would go in the other direction and I had a perfect match here, then I would add to the lower number whatever those degrees might be. So hopefully that makes also total sense. Verniers are kind of cool, the way they have put them together. Okay, now how do you do this practically in the field and then record it in the field notebook? Well, I've compiled a video that I took and went out there and did it for you and show you how strike and dip, after you set the declination, have your field notebook ready, have your protractor ready. How do you do this in a field, and how do you find some good spots to take strike and dip measurements? Let's watch. One of the most frequent measured things you can imagine in field geology is strike and dip. Every time you have a dipping bed, you can use this method, and you should record the data like something we just walked over. Don't leave out any of these opportunities to record strike and dip whenever you can. We can always chuck data later. It is difficult if you hiked into mountainous terrain to recollect or reconstruct data if you missed one. So measure more, throw out more instead of measuring less. Trails are often an excellent way to do strike and dip measurements as you hike along. Here you see good outcrop. Be careful not to look at the loose stuff over there. Something like that. This is of course just debris that eroded off. But here's a good outcrop. It looks like it's sticking right out of the mountainside. But I noticed something. There are two different dips. One you see here on this end, and there's another one you see right there. Totally different. What does it tell you? Well, it tells you that this is probably right here, not a dip, but a joint plane that kind of sheared off the material in this direction. So was a kind of like a hinge along this line. So this is not a good place to measure a strike and dip, because you don't know what is a true dip and what is just the joints that have fractured off. Now other places might be a little bit better as we hike along the trail. For example, this piece might be better. It seems to sticking out of the ground and has a very consistent slope in one direction. Once you identify the suitable place, for example this one here, where everything seems to slope and dip in about the same direction, it is time to go down and do some measurements. I think we found a perfect place here to measure strike and dip. Well, let's show you how this is going to be done. First, remember that your Brenton compass has this funny ring behind it, so it's not conducive to measure really low angles because you're bumping in on this ridge all the time. So therefore it's best to use your notebook and kind of align it the way you would think. It doesn't have to be accurate, the way that the strike direction is going to be. I'll assume it's going to be in this direction. Then you open your Brenton compass, and now you can use that edge of your hard notebook as a guide as you push down for your Brenton compass. You need to move it around, and remember the bullseye level inside needs to be adjusted. And once you get that just right with a little bubble inside, you can read off the Brenton. And in my case right now it is north 15 degrees east. That's my strike direction. I can even visualize it a little better, adjust my notebook a little bit to get kind of this reading right there. Now, to do the dip, we can do exactly the same thing. Remember, you have your little clinometer in the back. Again, you lay it down perpendicular now to the strike direction, and you move it until your bubble inside is level. And there you go. Now you can read off on that vernier the exact dip angle. What is left now is to transfer, of course, your readings into the notebook and draw them accordingly. Transferring all this on the notebook page, we had, let's make this one, of course, north is always up. In my little example here, my north arrow right there. And then
I want to use this as my north line. This is my, of course, west line, east line. And we said that whole thing was north, and it was 15 degrees to the east. So here's my little subdivision on that thing. So we're going to just turn this one until I get 15 degrees to the east right there. And I'm going to draw my strike symbol. That is my strike symbol. Little overemphasized, north, 15, east. Now we know it was dipping down this direction, exactly perpendicular. And of course we need to then write down, it's kind of dipping into the southeast quadrant right down there. But what is my dip angle? Well, we can consult our Brunton again, because we took the reading in case we forgot to write it down, which is not good. And you can see right here what it says on a little vernier scale right in the middle. It looks like on the lower part, we're going to use a lower part, it is 13 degrees to the southeast is my dip angle. And this is how you transfer the strike and dip measurements onto your notebook. Now, of course, I would also recommend you get the position and GPS units in the phone. Are really, really good to do that. Where did I measure this one? And there's my GPS coordinates. I'm using a program here called RockD. Even tells me which geologic formation I'm on, some of my measurement points, and I'm gonna transfer this one into the notebook. I didn't know what I used to measure that. Where soon I can even write down we are in the Cretaceous period, and we are in claystone. At least that's what the map tells me. And this is my RockD data.
Okay, hopefully that gave you a really, really good rounded review of what strike and dip is, the staple of many measurements, and really the heart of this class, using the Brunton compass to establish, in many instances, strike and dip values of areas you survey.